Hello everyone. Tonight we're going to continue and conclude our review of all elements from the periodic table of elements. We already went through element 1, hydrogen, to 29, copper, in the first two parts of this story. And we have almost 90 more elements to go through. But as we're going to see, many of them are less present and less significant in our lives, in our biology, or for industry. Some are even absent in nature. They do not occur naturally and only exist in labs. So we will go through some of them faster. But still, there are plenty of elements like gold or silver or uranium that call for lengthier introductions tonight. So please make yourself comfortable and let's get started with element number 30, zinc. Zinc is a metal that in some respect is chemically similar to its predecessor in the same group, magnesium. I already told you before about how different metals were obtained from ore by smelting or electrolysis, like in the case of aluminium. But how are these ores sorted? Because when ore is extracted from a mine, it is not pure, and from one site to another, the type of ore that is going to be taken from the ground, the elements it contains, can be very different. So the first step before the ore can even be processed is to separate it from rubble that will be useless. And there are different ways of doing this. It can be done by crushing and smelting, which is the usual treatment with iron ores. Another method, used especially for copper and precious metals or uranium, is called heap leaching. It uses a series of chemical reactions that absorb specific minerals, so that the one or the ones that are wanted are progressively separated and become usable. But the modern refining of zinc doesn't use these processes. It is achieved via another one called Froth flotation. Froth flotation is a process that separates minerals from worthless materials by exploiting their hydrophobicity, how much they are attracted or repelled by water. You know what hydrophobic and its opposite, hydrophilic, means. A hydrophobic material is one that is repelled by water and will not get wet or mix with water easily. Oil, for example, is hydrophobic. Hydrophilic is the opposite. It gets wet or melts very easily in water. Table salt, for example, is a typically hydrophilic compound. So the concept of Froth flotation is to apply different wetting agents to ore and filter it based on what floats and what doesn't float. And this way it is possible to create an industrial process that can separate automatically large quantities of raw materials. Raw material in the case of mining, but Froth flotation also serves in other areas and processes, like for the treatment of used waters or in paper recycling. It is not limited to mining. The development and the industrialization of froth flotation in the 20th century enabled greatly the use of ores that were not rich enough before to be used. Many mines could simply not have existed without it, or they would have been way more expensive to operate, because the ore they produced was not rich enough to be exploited. So this is how zinc ore is typically separated. Then it is roasted at high temperature to purify it, because it generally comes associated with sulfur in zinc sulfides. And finally, when most sulfur is gone, it is put in a solution to be obtained pure using electricity, like for aluminium. Zinc is resistant to corrosion and also relatively light, which is why it used to be employed to cover roofs, it still is sometimes, or to make gutters, but it tends to be replaced in that role nowadays by plastics or other elements that can be even lighter and also resistant to corrosion. In biology, zinc is also an essential element to life, from microorganisms to plants to animals. Like for a few other metals, life has evolved on Earth using the properties of zinc extensively. So, like calcium or iron, you find it in a lot of bricks that are essential to biological life. It is present in every single class of enzyme. You remember what enzymes are? They are very important to life because they act as catalysts that make many chemical reactions necessary to life happen. Finally, in our immediate environment, zinc is also in brass. It's alloy with copper. Brass was already in use thousands of years ago, during the Bronze Age. It could work as a substitute to bronze when zinc rather than tin was available. Except brass is softer than bronze, so it is not as suitable for tools or weapons. When it contains relatively more copper, brass tends to be bright and gold-like. This is why it is often used for doorknobs or drawer pulls. You probably have more brass and therefore zinc around you than you think. It is also common in zippers, in plumbing, because it resists well to corrosion, or in electrical plugs and sockets. Let's move on to element number 31, gallium, and 32, germanium, which are used essentially in electronics. Their properties are somewhat comparable to aluminium and silicon, respectively, but they are way less abundant and harder to collect, which is why they are mainly used in small quantities for electronical applications. Both of them, gallium and germanium, are also called metalloids. So what is that? It is like the concept of semiconductor. Metalloids are elements that have some of their properties identical to metals, and other properties similar to non-metals. They are in between. But we saw before that the concept of metal itself was unprecise. because what defines a metal, the capacity to conduct heat and electricity, could change with the conditions. Under certain conditions of pressure and temperature, many elements become conductive. Even hydrogen. I mentioned before metallic hydrogen, that is thought to be present in large quantities inside gas giant planets like Jupiter or Saturn. And metallic hydrogen is just regular hydrogen made conductive, metallic, by extreme heat and pressure inside these planets. So the boundaries, the definitions of metalloids are also a bit imprecise. They lack specificity. But the term is still used in the literature of chemistry. And some elements are still often called metalloids. Among the ones we have already reviewed are boron or silicon. Sometimes other elements like carbon and aluminium are also included in the group of metalloids. But this is much more controversial, because many chemists prefer to consider them as a non-metal and a metal respectively. So, as you see, the concept of metalloid is not very specific and well defined. But if you come across it, the concept behind is that it is an element that has some of the characteristics of metals without being one. Element 33 is famous for its toxicity. It is arsenic, another metalloid by the way. Arsenic as a poison has been known for centuries, thousands of years even, since antiquity. Actually, the name arsenic comes from a word in Syriac, a language that was spoken in the Levant 2000 years ago. It was adopted into Greek, arsenikon, then Latin, arsenicum. From there it became arsenic in French, and it passed to English as arsenic. As an element, it is used sometimes in alloys, not a recent use. During the Bronze Age already, there were cultures that added a bit of arsenic to their bronze to make it harder. And in industrial times, it was added to many products like insecticides, herbicides, or products to treat wood for its capacity to eliminate biological life. All these applications tended to decline in the past decades as the toxicity of arsenic was progressively recognized. Arsenic poisoning can be quick if a massive dose is ingested, or progressive over a long period of time if someone is constantly exposed to even small doses. It is very potent. But why is it so toxic? Because arsenic oxides have an affinity with compounds that are situated at the active sites of many enzymes. It disrupts the correct functioning of cells and leads to their death. So the signs of an arsenic poisoning are not very specific. The death of cells causes multiple organ failures. That's why, until the Middle Ages, arsenic was the poison of choice to discreetly kill people. It was impossible to say what the exact cause of death was. Poisoning would be suspected, obviously, but it was impossible to prove. Later, tests were developed, and arsenic poisoning can now be identified easily. But the bad reputation of this element for health was established, and rightly so. Element number 34, selenium, is also toxic in small doses. Trace doses of selenium are necessary for cellular function in many animals, including humans, but the level of toxicity is low. However, selenium is less abundant than arsenic, and that's why poisoning is very unlikely, except near places where it can bioaccumulate, in some aquatic habitats, for example, near chemical plants or because of farming. In these cases, selenium may accumulate in plankton or fish, in wetlands or ponds, and become dangerous if the fish are consumed by humans. Number 35, bromine, is the next element after fluorine and chlorine in the same group called halogens. I already told you about fluorine and chlorine. One particularity of bromine is that at standard conditions for temperature and pressure, it is a reddish-brown liquid. A particularity because out of 118 elements, there are only 2 that are liquid at normal conditions: mercury and bromine. Of course, there are plenty of liquids around us, starting with water, but these liquids are compounds or molecules. If you separate water into oxygen and hydrogen, these 2 elements at normal conditions will be gases. Number 36 is krypton, yet another rare gas after the ones we already discussed: helium, neon, and argon. Like them, it is a colorless and odorless gas that occurs in trace amounts in the atmosphere, and it is used in fluorescent lamps for the same reasons as its predecessors. Like other noble gases, it is very little reactive. After krypton, the following elements also share properties with their respective cousins of the same groups. Rubidium, number 37, is the following alkali metal, like potassium, sodium, and lithium. One difference it has with them is that it is denser than water, so it doesn't dissolve in it that easily. Instead, it tends to sink in water. Then there is strontium, number 38. Natural strontium is mostly not hazardous to health, because naturally it is found as a stable isotope, strontium-88. You remember, 88, this means that it has 38 protons in its nucleus, it is element number 38, plus 50 neutrons, for a total of 88 particles. But there is one isotope, strontium-90, with 2 more neutrons, and it is a dreaded product of a nuclear fallout. Strontium-90 appears as a result of the fission of bigger atoms, the fissions that provide the energy for a nuclear reaction. And strontium-90 is highly radioactive, which in other terms means that it is unstable. Strontium-90 nuclei are not energetically comfortable with their 52 neutrons, and this is what makes elements radioactive. Because they are not perfectly stable, they will tend to expel particles, energy, or even fission into 2 or more smaller atoms. What we call radioactivity is this behavior, this property of emitting energy and particles spontaneously. We will elaborate on that when we cover other elements. But strontium-90 is bad news because on top of being radioactive, it is easily absorbed by the human body, in a similar manner to calcium, which is its predecessor in its group. And that's why this particular isotope, strontium-90, is particularly dangerous in a nuclear fallout. After strontium comes element number 39, yttrium, which I already mentioned as a rare earth element. It is used in LEDs and various industrial applications, like the production of electrodes, of lasers, or medical applications. Number 40 is zirconium, a metal that is used either as an additive to metallic alloys for its resistance to corrosion, or as a refractory, that is to say, for its resistance to heat. Element number 41, niobium, is little known, and you may never have heard of it, but it is critical to many technologies. It is incredibly resistant to heat, with a melting point close to 2500 degrees. That's almost 1000 degrees more than iron. It is not the highest melting point of all metals. We will see that later, but it is considerably high. And it is used in jet and rocket engines for that property, as well as plenty of applications in very small quantities, optics, electronics, in the nuclear industry. It can serve in alloys to coat coins as an alternative to nickel. So we are surrounded with it, and we use it every day in very small quantities, but we barely know of this element. Its followers are also little known. Number 42 is molybdenum, another element with a very high melting point. It is used in alloys for that reason. Technetium, number 43, or ruthenium, 44, are rare metals. They are used also in very small quantities in very specific applications in nuclear medicine or as catalysts. Only a few tons are consumed annually in the world. The next one, number 45, is more famous. It is rhodium, one of the rarest and most valuable precious metals. In recent years, the ounce of rhodium traded around $15,000. This is 7 times higher, 7 times more expensive than gold. But why is rhodium so sought after? There is a minor use for it in jewelry, very rarely to make pure rhodium pieces. Not so much because of the price, because even at 7 times the price of gold there would still be buyers. It's also because rhodium is really hard to work with. It has a very high melting point, and it is not malleable like gold. So it is used, generally plated, on white gold or on platinum, to give these metals extra shine and a white surface, at time of sale only, because after this thin layer of rhodium will wear away with use. But jewelry is a small application for rhodium. A much larger quantity is used as a catalyst in automobiles, in catalytic converters. And there is no cheaper alternative to rhodium for that. Another rare and useful element is number 46, palladium, but the following is way more famous. It is number 47, silver. Silver has the reputation to be a precious metal, even though less so than gold. And indeed, if you look at the prices to put things into perspective, it is far less expensive than gold. So I told you that in recent years, 1 ounce of rhodium was worth $15,000. 1 ounce of gold, $2,000. And silver is around $22–23 per ounce, almost 100 times less than gold. Silver is another metal that has been used since antiquity, together with a few other metals, gold and also copper, iron, tin, zinc, lead or mercury. If it was more abundant than it is, silver could have a massive industrial use and even replace copper. Because of any metal at normal conditions, it has the highest electrical conductivity and thermal conductivity. So, in theory, silver electric cables could work even better than copper cables. But this would not be feasible because there is just not enough silver available. And by weight, silver is dozens of times more expensive than copper. So, technically or financially, it could not replace it. We can go fast on the 3 following elements: 48, cadmium, 49, indium, and 50, tin, because their properties are similar to their predecessors of the same groups in the table. I told you about tin already when we discussed the alloys of the Bronze Age. The same can be said of antimony, number 51, tellurium, 52, and iodine, 53. But let's stop for a minute on the following one, which is xenon, number 54. Xenon is yet another noble gas, and it has an isotope, xenon-135, that is closely monitored in nuclear reactors. But why is that? Xenon-135 does not occur naturally. It is too unstable, too radioactive to last. It is an isotope that appears in nuclear fission reactions. Of the different elements that are created when nuclear fuel fissions, typically this fuel is uranium, an isotope of iodine, iodine-135, is a common one. And this product of nuclear fission, iodine-135, experiences a form of radioactivity called beta decay. I told you before that radioactivity was like an umbrella term for different phenomena that so unstable atoms emit energy and particles. Beta decay is one of these phenomena, a type of radioactive decay in which a nucleus emits an electron and at the same time a neutron becomes a proton. So, if there is a change in the number of protons, the atomic number changes, it is no longer the same element. And I just told you that iodine was number 53 in the table, with 53 protons. If it acquires one more, it becomes element 54, xenon. Iodine-135 and xenon-135 have the exact same number of particles in their nucleus, except xenon has 1 proton more, and iodine has 1 neutron more. So, as you understand now, xenon-135 is like a subproduct of fission. iodine 135 appears first, and it transmutes into xenon 135. But why is it relevant to the management of a nuclear reactor? Because this xenon 135 isotope has one characteristic. It is neutron hungry. It tends to absorb more neutrons. And in a nuclear reactor, that's a problem, because it is the flow of neutrons that keeps the fission chain reaction working. The circulation of neutrons makes them available to be absorbed, caught by heavy atoms like uranium, which increases their instability and makes them fission, releasing more neutrons, and so on. The reaction sustains itself as long as there is fissile material available. But if you have xenon 135 eating too many neutrons, that can slow down and even stop the chain reaction. This is a well-known problem when operating a nuclear reactor. At the start, the reactor contains no xenon, but as more and more fission reactions happen inside it, in its first hours of functioning, xenon 135 piles up in the reactor as a product of fission, and it starts stealing the neutrons, which inhibits the chain reaction and will even stop it if nothing is done. So a nuclear reactor that would be turned on and left to its own device would stop by itself after a while. That's a phenomenon called xenon poisoning, and it is well known by nuclear reactor operators. In order to avoid xenon poisoning, the period when a reactor enters or re-enters service after fresh fuel has been loaded, or after a technical stop, this period is closely monitored to avoid xenon poisoning. By compensating the negative impact of xenon on the chain reaction with actions that stimulate fission, like withdrawing the control rods that also inhibit fission inside the reactor. And after a while, as xenon 135 disintegrates, an equilibrium is found between the creation and the destruction of xenon 135 inside the reactor. So the quantity remains stable and doesn't prevent the reactor from working. It just becomes one variable of its normal functioning. Xenon poisoning was an important factor in the chain of errors that led to the Chernobyl disaster in the 1980s. The operators of the reactor that eventually melted lost control of it because they tried to stimulate the reaction inside, not estimating correctly that the reactor was poisoned by xenon. They knew of this phenomenon, and in normal conditions of use, the reactor and all the rules and processes to operate it were designed to manage it. But they were making an experiment on the reactor, and they willingly removed several securities that were strictly forbidden to remove. They violated the rules of operation, and they saw the flow of neutrons lower than they wanted inside the reactor. So to stimulate it, they withdrew the control rods too much, and in seconds, xenon poisoning was overcome. The chain reaction grew exponentially, and the reactor became so hot that before they could react, the control rods were expelled, all control was lost, and the energy generated by the reactor reached hundreds of times the operational limit. following an explosion, a chemical explosion, that broke the building that contained it. The reactor and its radioactive material were exposed to the outside. A huge volume of particles were ejected, radioactive particles, in the atmosphere, and the inside of the reactor's tank began to melt. That's another story. But Xenon 135 played a part in it. Staying with highly radioactive isotopes, we have cesium, element number 55, which also has an isotope, cesium 137, that is a hazardous fission product. And after that, we have element 56, barium, a metal with very few applications. It is used sometimes as a radio contrast agent for X-ray imaging. It is also added in superconductors and some steel alloys. Elements 57 to 71, from lanthanum to lutetium, are called the lanthanides, and I told you about them already when I spoke about rare earth elements. They are all parts of this group, and chances are you never heard their names, because they are never mentioned individually out of labs or industrial plants. They include names like neodymium, number 60, promethium, number 61, europium, 63, or ytterbium, number 70. Number 72 is hafnium, and hafnium is also a rather confidential element, but one of its applications is as a neutron absorber, a neutron catcher, in the nuclear industry. I just told you about Xenon 135 absorbing neutrons. Hafnium also has that capability, and this is why the control rods of nuclear reactors that are driven inside the reactor to slow it down or withdrawn to stimulate it generally contain hafnium. It slows down chain reactions. Number 73 is tantalum, an element very similar to niobium that we covered before. They're from the same group, the same vertical line in the table of elements, and they share properties. Like niobium, tantalum is highly refractory. It resists to heat, and its melting point is the highest I have mentioned so far, 3000 degrees Celsius, or 5400 degrees Fahrenheit. That's twice hotter than for iron and 3 times copper, so it is really hard to melt. But it is not the highest of all elements. The highest known melting point belongs to a more famous metal. Element number 74, tungsten. Tungsten melts at 3400 degrees Celsius, and of all elements, it also has the highest boiling point, temperature at which it turns to gas. This boiling point is almost 6000 degrees Celsius, more than 10,000 degrees Fahrenheit. Tungsten is hard and dense. We rarely get a chance to manipulate tungsten, but to give you an idea, it is 1.7 times denser than lead, so it feels really heavy, and this density plus its hardness is the reason why it is suitable for military applications, especially for penetrating projectiles. A tungsten head is a good choice to pierce armor, more famous use of tungsten, but it is disappearing in our homes at this point, was for light bulb filaments. For most of the 20th century, light bulbs used filaments, generally of tungsten, for its high melting point. The electric current in the filament made it heat up and emit light. The inside of the bulb was filled with a noble gas, typically argon, to avoid combustion, for reasons that you now understand, because noble gases are very little reactive, and the atmosphere inside the light bulb was free of oxygen to avoid combustion of the filament. Element 75 is rhodium, one of the rarest elements in the Earth's crust, about 1 part per billion, which in other words means that to find 1 gram of rhodium you would have to process, in average, 1,000 tons of Earth's crust. It has a few industrial applications, especially for jet engines, because it serves in superalloys with nickel to make combustion chambers. The two following elements, osmium, number 76, and iridium, number 77, are famous for their density. Osmium is the densest element known among the ones that occur naturally. It has a density of 22 grams per cubic centimeter. For comparison, this is 3 times more than iron, and twice more than lead, and 22 times more than water. Water is the benchmark for density. So what it means, said differently, is that for the same volume of water and osmium, the block of osmium would be 22 times heavier. Osmium is also even rarer than rhodium, and is estimated to be the rarest of all precious metals. So you could think it is going to be extremely expensive, but not that much, because it has very few applications. It doesn't look particularly shiny. It is just silvery, like many metals, and so the price per ounce, when there is one, because there are very few transactions, is between a third and half the price of gold. Iridium is a bit more frequent, but still confidential. World production and consumption of iridium is around 7 tons per year. That's really not much. But their follower, number 78, is way more famous. It is platinum. In monetary terms, platinum is less expensive than gold nowadays. But there was a time when it was up to twice as expensive, and it remains a precious metal that looks silvery white. It has more industrial applications than gold. And its most remarkable characteristic is that it is one of the least reactive metals. These metals that do not react easily will often be found pure in nature, which is logical. They did not combine with others. Gold and others we already reviewed, like rhodium, palladium, and osmium, have the same characteristic, and they are sometimes called noble metals because of it. Noble in the sense that they are lowly reactive, like for noble gases. And gold is the following one, number 79. Some of the characteristics that make the appeal of gold, like its absence of corrosion, so it remains shiny, come from its low reactiveness. It is also resistant to most acids. There is the exception of aqua regia, this mixture of hydrochloric and nitric acid that we talked about earlier. And gold is relatively rare, but there are many rarer elements than gold. The high monetary value of gold comes from the combination of its visual appeal. It doesn't get dark because of corrosion. It is yellow, contrary to many metals that are just grey, and it has built up a reputation, an aura as a precious material after several thousand years of being a symbol of wealth and power around the world. It didn't happen in every single culture, but in many of them, from America to Africa, Europe and Asia. Everywhere gold acquired a particular, a specific status, enough to make it an ultimate symbol of value. And 90% of demand for gold is linked to this. 50% of produced gold goes to jewelry, 40% as a reserve value, as an investment, bearing in mind that a part of the use in jewelry is also intended as a mean of stocking value. And only 10% goes to industry, mainly for electronics. There is a bit in all computers, for tooth restoration or gold leafing of ornaments. We still have a few famous elements to go through, like the following one, number 80, mercury. I told you earlier that bromine and mercury were the only two elements known to be liquid at normal conditions. Mercury is the only metal, because bromine is not a metal. And it has various uses that are familiar, like inside thermometers. But it is also known as an environmental heavy metal. Heavy metal is another concept that is loosely defined. It can refer to the density of metals, as opposed to lighter metals like aluminium, and in that case, mercury is a heavy metal. It is pretty dense. But in health and environmental terms, heavy metals are elements that can be highly toxic, either pure or as parts of compounds, and that accumulate in the environment or in the food chain. Mercury is one of them, together with lead, chromium, arsenic, cadmium. I already highlighted the toxicity of several of them. Mercury in particular can cause damage to the central nervous system. And another highly toxic element when it comes as salts is thallium, number 81, often used in history as an alternative to arsenic to poison people. Thallium is sometimes called the poisoner's poison or the inheritance powder for that reason. Number 82 is also toxic and another heavy metal that has probably killed on a much larger scale than arsenic and other toxic elements I mentioned before. It is lead. Lead was historically relatively easy to retrieve and abundant. It has a high density. It melts at a very low temperature, just a bit more than 300 degrees Celsius, so it made it a metal of choice, not too expensive, easy to use, for a large range of applications in construction, plumbing, paints, batteries, as an additive to gasoline. Its toxicity has been known since at least the ancient Greeks and Romans, who documented it. It caused a syndrome called Saturnism, but it was downplayed for a long time. I remember when I was a kid, there were still applications for toys, like little soldiers or figurines, or plumbing, that must have been forbidden now, but were common in the 1970s and 80s. Because lead is a potent neurotoxin that damages the nervous system and accumulates in bones and soft tissues. It is not spectacular, but over time it affects general health. It attacks the heart and kidneys, and what it is most known for, it causes neurological disorders. Element 83 is bismuth, a metal that can be sometimes used as a replacement for lead, because it is way less toxic. And after that, with element number 84, polonium, we enter the territory of heavy atoms. The more we advance, the more protons they have, and also the more neutrons they tend to have in their various isotopes. So they are heavier and heavier. Heavy atoms that have a tendency to be unstable, that is to say, to decay, to emit particles and rays. I mentioned earlier the radioactive beta decay, with the example of iodine 135 turning into xenon 135 in nuclear reactors. Beta decay is when an atom emits an electron, or its opposite, a positron, and a neutron becomes a proton. Another type of radioactive decay is alpha decay. It is when the nucleus emits what is called an alpha particle, or a helium nucleus, 2 protons and 2 neutrons. Instability of an atom may lead to radioactive decay or even to fission, when the nucleus breaks apart into 2 or more atoms with a smaller atomic number, of course. So, under the umbrella of radioactivity, we have different phenomena that happen at the atomic level and lead to the emission of radiations, of energy like heat, and particles of different nature and sizes. It can be protons, neutrons, electrons. From polonium and after, all atoms have varying degrees of instability. Sometimes it is not very pronounced, and they decay very slowly, over millions of years. Other times, they are very unstable. This depends on the elements and their respective isotopes. But contrary to lighter elements that we have just gone through, that can have radioactive isotopes and other isotopes that are not radioactive, above atomic number 83, 84, everyone is radioactive to an extent. And it begins strong with polonium, which only has highly radioactive isotopes. The discovery of polonium in 1898 is one of the discoveries that made the fame of Marie Curie. This is why it is called polonium, after Poland, her country of birth. She became the most prominent of the early explorers of radioactivity, a phenomenon that was barely understood in the 19th century. Element number 85 is astatine, which is the rarest naturally occurring element of all elements in the Earth's crust. Why is it so? Because it appears only as the decay product of heavier elements when they lose protons, and all of its isotopes are also short-lived. The most stable one has a half-life of 8 hours. Half-life is a concept used to illustrate the radioactivity of elements. It is the time it takes for half a quantity of radioactive material to decay. So a half-life of 8 hours means that in 8 hours half a given quantity of an element will have decayed. That is short. The half-life can range from seconds to millions of years. The shorter, the more unstable and radioactive an element is going to be. So the consequence of this instability is that no solid sample of astatine has ever been observed. Even if one could be gathered, it would be immediately vaporized by the heat of its radioactivity. So we don't know what astatine would look like at normal conditions, because it cannot really exist as a solid at normal conditions. After astatine comes a new noble gas, number 86, radon, which is also radioactive under all its isotopes, contrary to its predecessors in the group of noble gases. The longest half-life of the natural radon isotope is almost 4 days, but that remains short, and any radon in a lab has to be synthesized, obtained by decay of heavier elements or another method. After it come several more radioactive elements: 87, francium; 88, radium, another discovery of Marie Curie; 89, actinium; 90, thorium, which is more stable than its neighbors in the table. It is still radioactive, but it has one isotope, thorium-232, so that's 90 protons plus 142 neutrons. That has a very long half-life, a half-life of 14 billion years, about the estimated age of the universe. So this particular isotope is only very lightly radioactive, enough to not be dangerous to humans, and it has a few industrial applications. Number 91 is called protactinium, and after it come the two last elements of the table that have a degree of fame. Number 92, uranium, and number 94, plutonium. In between there is neptunium with number 93. Uranium is the fuel of choice for nuclear power plants and weapons. But why is that? Because some isotopes of uranium, essentially uranium-233 and 235, can maintain a sustained nuclear reaction when they are in sufficient concentration. And their fission is the one creating all the subproducts that appear in the reactor. And uranium was present naturally in sufficient quantity on Earth to have a functioning industry based on it. Even though natural uranium available in nature is another isotope, uranium-238, which needs to be processed, enriched in uranium-235, before it becomes usable nuclear fuel. Because uranium-238 is not prone to fission that easily. Plutonium, number 94, is the last element that can occur naturally without human intervention, but in very small quantities, and all the plutonium used is obtained artificially via the transformation in nuclear reactors. The exact term is transmutation of uranium atoms. They only need to gain 2 protons to become plutonium. That is what also made the appeal of uranium for military use in nuclear weapons. Uranium is said to be fertile because it can be turned into plutonium, and plutonium is particularly prone to participate in fission chain reactions. Some of the first atomic bombs already had plutonium cores. After plutonium, all elements from 95, which is americium, to 118, Oganesson, had to be obtained completely artificially after their properties had been theorized. As far as we know, the conditions for their creation do not exist in nature, and they have been synthesized and classified for the sake of fundamental research because they have no significant applications. They are very unstable. These are huge atoms with hundreds of particles. So, to conclude our talk for tonight, I will go through their numbers and names. It's a bit like counting sheep. Let's go. So we have number 95, americium, 96, curium, 97, berkelium, 98, californium, 99, einsteinium, 100, fermium, 101, mendelevium, 102, nobelium, 103, lawrencium, 104, rutherfordium, 105, dubnium, 106, seaborgium, 107, borium, 108, hassium, 109, meitnerium, 110, darmstadtium, 111, oranginium, 112, copernicium, 113, nihonium, 114, flerovium, 115, moscovium, 116, livermorium, 117, tennessine, 118, Oganesson. We have finally completed our tour of the periodic table of elements, and I hope you enjoyed this little exploration journey of the elements. I'll be back soon with another story, one of historical mystery, and in the meantime, sleep well, sweet dreams, au revoir.